At a high school, there are 12 players on the school basketball team and 8 players on the volleyball team. And how many players would show up at a party if exactly 5 students play on both teams? So the idea behind this is to avoid double counting. Helps us avoid double counting. Okay, so let's just kind of look. We're going to draw a Venn diagram for this situation. So here we have our box for the Venn diagram with S for universal set. We have a blob and a blob. There's some intersection with the basketball team and a volleyball team, and we know that 5 players play on both, right? So there's an intersection of 5. Okay, so we know there's 12 players on the basketball team, so that must be 7 more people there for a total of 12. And 8 players on the volleyball team, so there must be 3 more people there. So how many people would show up? Huh? 15, right. At most 15 players would show up. Okay, the number. Now this is going to be the formula. The number on the basketball team union the number on the volleyball team equals the number on the basketball team plus the number on the volleyball team, but we've got double counting because if we add up 12 to 8, we get 12, right? So we have to subtract the intersection basketball team intersection volleyball team. So you have 12 plus 8 minus 5 is equal to 15. So no matter which way you look at it, whether you want to draw your Venn diagram and add them up or use the formula, it's up to you. Alright, so principle of inclusion exclusion for 2 sets, A and B. The number in A union B equals the number in A plus the number in B minus the number in A intersection B. The number of elements in the union of 2 sets is being counted. Alright. Alright, let's look at another example. A researcher looking for 2 characteristics known as X and Y examines 100 insects. For those of you who will be going into science and research, this is the type of thing you do. You might examine DNA of insects or whatever. It's quite fascinating stuff, but it can be very tedious as well. Every insect every insect has either X or Y or both, but the researcher cannot determine directly whether an insect has characteristic Y alone. She finds that 48 insects have X and 23 have both X and Y. How many insects have characteristic Y? So let's take a look at this. We'll do A. Okay. The number in X union Y equals, we'll just use our formula, the number in X plus the number in Y minus the number in X intersection Y. Okay, so what's the number in X union Y? Does anyone care to tell me? 100, perfect. And the number in X, so 48 insects have X. And we don't know the number in Y alone, but we do have, see, 23 have both X and Y. Remember, 99% of the questions, if you have a problem-solving question, it'll say and. And if you know, for intersection, and for union, it will say or. plus the number in y. We don't know that. We have to calculate that. But we do have an intersection of 23. So we can just solve for the number in y equals 100 minus 48 plus 23, and that equals 75. So 75 insects have characteristic y alone. Mm-hmm. Huh? Oh, my bad. Thank you for that clarification. You got to keep this old lady on the ball, you know. You just have to do that. Okay, thank you very much. All right. Oh, how many have y only? Well, that's a good point. I'm glad you brought that up. So anyway, let's maybe do a Venn diagram, see what we can do. We can do, there we go, S. So we'll do X and Y and see if we can isolate having Y alone. So 23 have them both, and we know 48 have X, so 48 minus 23, right? So see this circle here representing X should add up to 48. And Y alone, well, what do you think? How are we going to calculate Y alone? So we can do some subtraction. There's 100 in total. We know all of them have X or Y, so there's no insects that will be outside the union, right? Minus 48 basically, or minus 25 minus 23, and that is equal to 52. So Y alone is 52. 52 insects have Y alone. Or Y only. I don't know why I'm into alone. Okay, Y only. There, how's that? Yeah.
Since we are certain that an insect has either X or Y, shouldn't the X and Y union be the entirety of S?
In this case,
So
yes.
there are no elements outside X and Y.
Yeah, there's no elements outside the union. So this is all.
So should we leave that space, or should we?
Yeah, so I guess what we're saying is X union Y not is equal to the empty set.
So when we're drawing the Venn diagram, do we leave this space, or do we just?
Oh, you just leave it like that.
I see.
I think in the next example, we'll put some numbers in that space.
I see.
Yeah, to the empty set. Or the number in X union Y not equals 0. Or you could have wrote it like this, right? Empty set. Either way, you can write it either way. No, no, I just had a question up here and I was just trying to show off a little of my additional knowledge, that's all. Whatever. Okay. What happens when we have 3 sets? Ooh. The formula becomes much more complicated. So what happens is the number in A union B union C is number in A plus number in B plus number in C minus the number in A intersection B minus the number in A intersection C minus the number in B intersection C, and then we subtracted too much, so now we have to add back what's common to all 3. You believe me? You don't want to take my word for it? Huh?
Let's draw a Venn diagram.
Yeah, it's really hard to illustrate because of all the, so just, so we go number in A, number in B, number in C. So this central part was added in 3 times. So we're going to subtract the intersections 1, 2, 3, and then all now that's empty. Once you subtract the intersections, that little space in there is empty, so we have to add it back in. Roughly. Okay? According to a representative of the Student Services Department at a high school of 100 students currently taking OAC courses, the distribution is as follows. Calculus 52, AG 38, Finite 41. This course used to be called Finite. It used to be a lot harder. So you guys were born in a good era. I'll tell you that. The intersections are here. Notice and finite, and all 3 is 8. Draw a Venn diagram to illustrate this. So let's do A first. S. Okay, so there's 100 students we need to know about, right? Working backwards. Oh, hold it. Let's do this. I'm just gonna, that's calculus, that's algebra, geometry, and finite. So working backwards because we have to take into account uh, 8 students take all 3. Let's see. Finite and calculus is here in this blob, and there's 15. So in this little intersection here, we need 7 more. You have to work backwards. Algebra geometry is 22. We already have 8, so we need 14 more, right? Finite math, finite, oh, algebra and finite. I think I did that one. No, I didn't. Did I? Yes, I did. No, let me double check. Okay, algebra, geometry, that one's that. Algebra, geometry, and finite is 17. So I guess my eye skipped, did it? I think it. Sorry, I think my eye jumped a little bit. I'm going to take off my trifocals because I think I'm just kind of. Let's just double check. Finite and calculus 15 were good. Algebra, geometry, algebra, and algebra and the 14 goes here, right? Yeah. And yes, do you disagree with some? Okay. Okay. Algebra and finite goes here, and that should be 9. Okay. Finite math, this has to add up to 41. So 41 minus 7 minus 8 minus 9 is 17. Algebra geometry is 38, so 38 minus 14 minus 8 minus 9 is 7. Calculus is 52, minus 22 is 30, minus 7 is 23. Can somebody add up all these numbers for me? Does that add up to 100 or no? It adds up to 84. Yeah. So I was hoping this would not add up to 84, but something else. Are my numbers wrong? Let me double check. Anyone get a different answer? It should be, you got 85? That's what I got. So how many go out here? So 15 do not take math. Okay, so we did diagram A. How many study only algebra and geometry? Well, you pick that up right there. The only is right there. Okay, I want to do C using the formula just to illustrate it. I think you know from the diagram this is a calculus, union algebra, union finite. I think you know that already, and that adds up to 85, but just to illustrate with the formula, the number in calculus, union algebra, union finite equals the number in calculus plus the number in algebra plus the number in finite minus all three intersections. Let's see. We got CA, we A and F. Okay, thank you. Minus the intersection and all. Oh, add the yeah, plus, you're exactly right. C intersection A intersection F. So the number in calculus, 52, 38, 41, minus 17, minus 2, 2, minus 15, plus 8. And that equals 85. Now, if we use the Venn diagram, just to make sure everybody's on board, the number in C union A union F is, we just added all those up, right? 23 plus 14 plus 8 plus 7 plus 7 plus 9 plus 17 equals 85. So 85 study math only. Oh, 85 study math, period. Are we good? Can you handle another lesson? It's kind of a review of stuff you know from grade 11 as well as...
Let's do it.
Let's do it. Okay. You'll like it. It's kind of different. The numbers that form the patterns in Pascal's triangle can be found using combination. The combination n minus 1 c k minus 1 or n minus 1 choose k minus 1 gives the element in number k in row n of the triangle. For example, the fourth number in the sixth row is 5 choose 3 equals 10. Fourth number in the sixth row is 5 choose 3 equals 10. So let's just look at this. I think you know that this can be represented by 0, choose 0, right? Just like you have it down here. 0, choose 0 is 1, and these two numbers are 1, choose 0, and 1, choose 1. Do you remember that from grade 11 a little bit? But you can find every number here. So notice this is row n equals 6, but it's really the 7th row. 1, 2, 3, 4, 5, 6, 7. And this is 1, 2, 3, 4, 5, 6, 7. So if this is the 7th element, yeah, yes, thank you. You're exactly right. So let's just do another. 2, choose 0, 2, choose 1, and this one would be 2, choose 2. So this is the 7th element, right? 1, 2, 3, 4, 5, 6, 7, and it's in the 7th row, and it would be, this would be represented as 6, choose 6. It's that 0 that you know, these zeros throw it off a little bit. Because this is the 5th element in the 5th row, but you know, we can address it as row n equals 0, n equals 1, n equals 2. So note that any row of Pascal's triangle, those entries equidistant from the end are equal. So the way we can calculate that is n choose r equals n choose n minus r, right? And we can prove that because we know the formulas, right? Left side equals n choose r, that equals n factorial over n minus r factorial, r factorial. Right side equals n factorial over n minus the whole thing, n minus r factorial. And that's n factorial over r factorial, n minus r factorial. So left side equals right side. I just plugged in the formula. Maybe I should have wrote this down. N choose r equals n factorial over n minus r factorial, r factorial. Right? That we're using that the combinations formula to prove. I did that a little quickly. Is there anything you would like me to go over? No? Do you want me to leave it? If you could talk louder, because these things on my ears block my hearing. Just to make sure I don't miss any of your questions. Good? To what other expression in the form of n choose r is each of the following equal? What do you think? What is this equal to? (21) choose 21 n choose n minus r. So this is going to be 21 choose 13. So that 8 and 13 should add up to your top number. And this guy's just going to be 9 choose 9 minus a. And that's just getting at that point where when they're equidistant from the ends on the Pascal's triangle, they're equal. Okay. If we look at Pascal's triangle, just as a review, you know this is 1, and 1 plus 6 is 7. If we want to get the n equals 7 row, or the 8th row, but it's the n equals 7 row, we just take the two terms immediately above it and add it together. We can check these values by just going evaluating 7 choose 0 equals 1, right? There are 7 ways to choose one thing when you have 7 things. And then this number is just, the third number is 7 choose 2, and that equals 21. The fourth number is 7 choose 3, and that equals 35. And now I think you can see we're getting into values that's equidistant, so their values should be equal. Now the 21, 21, that's going to be 7 choose 5, right, is 21. And 7 choose 6 should be the same as 7 choose 1. There are 7 ways to choose 6 things when you have 7 things to choose from. And 7 choose 7 is the same as 7 choose 0, and that equals 1. That Pascal was quite the man, eh, when it came to math. Tell me, what expression in the form n choose r would we predict to be equal to this? 23 choose 18 plus 23 choose 19.
23 choose 5 plus 23 choose 4.
Oh, that's funny.
Yes.
Yeah. What about if in just a single expression?
24 choose 18.
It would be what?
24 choose 18.
Yeah.
19.
Yeah. So if we did an example, so this would be 6 choose 0, 1, 2, 3. 6 choose 3 plus 6 choose 4 is equal to 0, 1, 2, 3, 4. 7 choose 4. Right? We're going into the next row, so instead of 6 it's a 7, and pick the larger one. If it's 3 and 4, then pick the larger of the two. So what would this guy be? 65 over 30. Good? Okay. The generalization of this pattern is this, and this is known as Pascal's theorem, where any term equals the sum of the immediately preceding two terms in the previous row. So let's just prove that. Using n choose r equals n factorial over r factorial n minus r factorial. Did I go too fast? Did you want me to leave that up there for a minute? Okay. Okay, let's do it. Let's just manipulating this equation algebraically, and left side equals n factorial over r factorial n minus r factorial plus n factorial over r plus 1 factorial n minus r plus 1 factorial. Okay, let's look at what the right side will look like, because I think the right side is simpler and it'll give us a hint to do the left side. N plus 1 factorial over r plus 1 factorial n plus 1 minus r plus 1 factorial. So plus 1 minus 1 is 0, so we're left with n minus r factorial. So if we were to just simplify this, let's see, n plus 1 factorial over r plus 1 factorial n minus r factorial. So there's nothing more we can do here. So our goal is to make the left-hand side look like this. Let's simplify this guy. N factorial over r factorial n minus r. Leave a little bit of a space because we're going to have to do some multiplication.
Because it's in how come it's r plus 1 factorial on the bottom of this?
Here was it?
Never mind, sorry.
That's okay. This is going to be n minus r minus 1 factorial. Ah, I didn't leave. I bet you I can white it out and make a little bit more room. Okay, we gotta make this side look like this side. So we need this common denominator. Look, so let's compare. Ooh, if I look at this, we need these denominators. N minus r, got it. Oh, but this one's r and that's r plus 1. What can I do to bring this up to r plus 1 factorial?
We multiply r plus 1.
Okay, sounds good to me. Let's compare. R plus 1. Ooh, this one's n minus r minus 1, and this one's just n minus r. So what do we multiply this guy by?
So n minus r.
You are on a roll. Awesome. How's that? Okay, so now we have n factorial times r plus 1 all over r plus 1 factorial n minus r factorial plus n factorial over r plus 1 factorial. So n minus r minus 1, we multiply it by 1 up from that, which is n minus r. So this becomes n minus r factorial. And I can't forget the n minus r, right? So we have a common factor of n factorial. So now we have our common denominator. So it's n factorial times r plus 1 plus n minus r. So now we have n factorial times n plus 1, because r minus r is 0, all over r plus 1 factorial. We can further simplify because this is now sorry, numerator here. N factorial is factored out. So I got this times that is that, that times that is that, that times that is that, that times that is that. We got it. It's all covered. Okay, so this is n plus 1 factorial all over r plus 1 factorial n minus r fact. So left side equals right side. So example 6 and 7 are fun. So they give you this arrangement. How many ways are there to spell George Paulia? We're going to use Pascal's the patterns in Pascal's triangle. So to get to E, there's only one way to do it, right? You can only go from G. And to get to E, there's only one way. To get to O, there's only one way because you can't go crisscross. It has to be diagonal, sort of this diagonal kind of thing, but you can't jump. So to get to this O, you can only go from the E, but to get to this O, you can go from two E's. So there's two ways. And to get to this O, there's only one way. So there we have G-E-O, 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 G-E-O. There's four right there in total. Okay, let's keep going. To get to this R, there's one way. To get to this one, there's 1 plus 2 ways. So it's 3 ways. To get to this R, you can come through here. So there's 3 ways, and that's 1. So it's 1, 3, 3, 1. Let's keep going. To get to this G, you have to come down from these, you can come down from these two R's, so that's 3. 3 plus 3 is 6. 3 plus 1 is 4. Did I add wrong here? I think so. This should be a 4, right? So across the G's we got 4, 6, 4. Four plus 6 is 10. 6 plus 4 is 10. 10 plus 10 is 20. Right? Now to get to this O from the P, there's just 20 ways. And to get to this O from P, there's 20. To get to the L, there's only, that L is only 20, but 20 plus 20 is 40, and 20. Now to get to this Y is 60, and to get to this Y is 60. 40 plus 20 is 60, so that's 120 ways. 120 ways to spell George Paulia. Just using the properties of Pascal's triangle. Similarly with the checkerboards. You can move this, you know, see how they tell you can move one square at a time diagonally? You can only, so this guy cannot move in a black spot. How many different ways are there to get to the opposite side? Well, it's one way to get there, one way to get there. One way, one way, one way. 2 ways to get there, right? He could go like that, or he could go like that.
Oh, can you go back?
No.
Only one square diagonally up.
Yeah. So to get to this square, there's only 2 ways. Here's 3, and we're done that row. 2 plus 3 is 5. 3 plus 1 is 4. 5 ways. 5 plus 4 is 9. 4 plus 1 is 5. So if you were to add those up, there are 19 ways to get to the opposite side. Can I explain anything? Okay.